Hello. Hi, everyone. How's everybody doing? Are we at least mildly excited about looking at redox half equations? Hello, Percy. No responses. Oh. Is there going to be a live stream on Hess's law? Well, at the moment, we're sort of asking on Insta what people are finding most difficult. Hey, T-Boy. And then doing those topics. If Hess's law is sort of something that comes up a lot, then we can do Hess's law. So Aisha, if you can get everybody to sort of like bombard our Insta or bombard the chat here with requests for Hess's law, then we can do Hess's law, essentially. Does anybody have any tricky topics that they've sort of been hoping to see come up? Hey, Neha, is that right? Neha or Neha or Nea, possibly Nea. Let me know if how to pronounce your name. That would be helpful. Can I go over organic? Organic will come up soon. Neha. Okay, cool. Perfect. And periodicity, organic will definitely come up because there's been plenty of requests for organic. It's just sort of about thinking of the best way to do it because obviously it covers a lot of stuff. So that's something to think about. Okay, why not? Let's get started slowly. Periodic trends. Okay, so lots of people would like to do some periodic trend stuff. Transition metals, redox titrations, buffer calculations. All right, loads of things. Okay, so at this point, we should probably, I should say, that is a good amount of suggestions. Go ahead and when we sort of ask on Insta what you guys want to do, make sure you like put those things forward. And if you see people commenting, sometimes we do YouTube polls. If you see people like liking a comment, we also do look at how many people have liked the comments for a request. So like the comments for things that you definitely want to cover. What is a redox reaction? It is a reaction where you have an oxidation and a reduction happening at the same time. We're going to be looking at that now. So I'm going to go ahead and share the presentation with you all so that we can get started. All right, can we all see the presentation on redox half equations? Is it all visible? Yeah? Wicked. All right, so the objectives today, obviously, because these are only sort of like 45 minutes long, we are just looking over a sort of small section of redox. And we're going to really quickly go through the rules determining oxidation states. So we're not going to spend all of our time practicing that because the main point is to be able to use that to construct half equations from full equations, and we'll also go backwards and construct full equations from half equations. So that's the idea. We're specifically looking at the stuff we need to know for that skill. So spec-wise on OCR, that's just these two bits at the bottom. So writing half equations, combining half equations for overall redox equations for OCR. OCR sort of spreads things out quite a lot. So it's everything on here except for this bit. So there's quite a few bits on OCR that covers. And then for Edexcel people, it's just these bits at the bottom that we're looking at today. So just like a really tight, what skills do we need to know to have to do that? Okay, so the first thing we want to be thinking about are our oxidation states. So how we work out the oxidation state of a compound. Do you have OCRB? So it's not specifically for OCRB. Is it Parvati or Parvati? Parvati. It's not specifically for OCRB, but it covers the same things that OCR A and B will do. This is just like a skill that is on all of the syllabuses, so I wouldn't worry about the fact that it's not specifically for OCRB. but no, I don't have the actual spec points up. Okay, oxidation states. So we're trying to, I want you guys to sort of like just at me, just like send me the rules you think you know about oxidation states. So we've got all of the sort of, we've got a list here of a bunch of oxidation numbers for compounds. Yeah, so T-Boy says elements have 0 oxidation state, which is correct. So if you have a pure element in a compound, so like let's say we have like Cl2 or something, the Cl, the chlorine, is going to be, the oxidation state is always going to be equal to 0. And thank you, Jackie, because that is exactly what I was looking for next. So if we don't have a pure element and we have some kind of charged molecule or charged particle, the oxidation state is going to equal to the charge. So ions have oxidation states equal to their charge. So this could be things like single things like Cl minus, where it's just a chlorine ion, which the oxidation state would be -1, or it could be like whole compounds. So it could be something like dichromate with a 2-. So all of those things would end up adding up to 2-. So it could either be just for a single thing, or it could be the sum of all of the oxidation states must be equal to the charge of 2-. Aisha says, do you need to look at which one is stronger to obtain or lose electrons? Not at this point. At this point, we're just looking at the rules for oxidation states. What you're thinking about, Aisha, is electrode potentials, which is what we looked at last time. How do you know the oxidation state of an element? Not usually stated in revision guides. It's always 0. For any element on its own, it's always 0. For any compounds, this is what this this table on the right hand side is for. So I'll come to that in just a second. But if we have a compound, what does that add up to? Yeah, so Parvati or Parvati, if you could give me a pronunciation guide for your name, Parvati/Parvati, that would be great. Yes, so as Parvati says, if you add up all of the oxidation states for a neutral compound, it's going to be equal to 0. So neutral compounds add up to 0. And I've got quite a comprehensive look at the different oxidation numbers for things. The main ones, though, that you need to know are oxygen, which is -2. That comes up a hell of a lot. Hydrogen, which is +1. Fluorine, which is -1. And then your group 1 and 2 and aluminium. So I would say these ones, if you're going to sort of like concentrate on remembering things, it's these 6 that are most important. So yes, hydrides are in there. So if you are in year 13, you will have come across the compounds sodium borohydride or lithium aluminium hydride when you're looking at reduction reactions. So if you've seen those, then those hydrogens are hydrides. So they have a -1 oxidation number. But if you're in year 12, you won't have come across those yet. So I wouldn't be too worried about if you don't know what a hydride is at this point. Is everybody comfortable with those rules? Because if we're comfortable, we're going to move forward and have a bit of a practice at applying them. We feeling good? Yeah? Okay. Wicked. Let's go ahead and have a practice. So the first thing I want to do is work out what does the stuff next to the Cl mean. So Cl chlorine is generally a -1 unless it's bonded to fluorine or oxygen. And then the rules for fluorine and oxygen take precedent. So we're just keeping that in mind. So there are compounds like ClO, Cl2O, where you have the oxygen taking precedent over the rule for chlorine being -1. So just keep in mind if you've got fluorine or oxygen in there, it's not necessarily -1. Usually is, but not necessarily. Does that make sense, Aisha? Yes, no, maybe. Let me know if it doesn't, and I will have another go at explaining. Okay, so the first thing we're going to do on this page is we're going to look at the oxidation states for all of the compounds on the first half of this equation. So we just want iron, oxygen, and aluminium. Yes, I did mean the EX. Yes, thank you. That was a typo. I appreciate, I should change that. Thank you, Aisha. Which ones are more important if you're given H2O2? So in H2O2, oxygen is -1. So you just have to memorize that. So I've got my list of exceptions. There are exceptions on that list. So if you want to screenshot that list of things so that you have them permanently, then go for it. So the only reason I sort of like put squares around those specific ones is because they're the ones that come up the most often. So those are the ones you really want to drill. The rest of them come up much less often, but you should still know them. Okay, so Jackie and Fassi have said that we have a +3 oxidation state for iron, which is correct, right? Because we always know, we'll start with oxygen. And if you remember from the other page, oxygen is always what? Or almost always. -2, yeah. So if we're trying to work out the oxidation state for iron, we're going to need it to add up. We're going to need Fe2O3 to add up to what? 0, yeah, because it's a neutral compound, so it has to add up to 0. So if we've got 3 oxygens, that means we're going to have -2 times 3, which is going to be 6. And then we have 2 Fe, and that has to add up to 0, which must mean that our Fe has an oxidation state of +3. Does that make sense to everybody? Or is there anybody that doesn't make sense to? Cool. If anybody's ever confused, Mariam, is that it doesn't make sense, or is that it does make sense? It does. Okay, cool, perfect. All right, and lots of you have already said that aluminium is 0, and you are correct because it is an element, so it must be 0. So can you have fractional oxidation states? No, because as we're going to talk about in a bit, oxidation states represent an electron, and you can't have half an electron. You can only have a whole electron. But we'll be talking about that in a minute. But that's a really good question. Okay, so in the next, we want to be looking at our products. So in our products, we have again oxygen, and what's our oxidation state for oxygen? -2. What about Fe3O4? So Parvati, if you think about it, not all compounds can exist, right? So not everything is an existent compound, specifically because it needs to share electrons in different ways. So like if you're coming across something that sort of demands an oxidation state that is fractional, you are possibly looking at a compound that doesn't exist. Okay, so I'm getting lots of people saying aluminium is 0. Aluminium is not 0 in this case. So remember now aluminium is with oxygen. So we're going to need to work out the oxidation state of aluminium in the same way as we worked out in iron. Yeah, so getting lots of people saying aluminium is +3. So let's have a look at why it's +3. That is correct. So again, it's going to have to add up to 0 because it's a neutral compound. And we're going to have 3 oxygens again. So it's going to be -2 times 3, which is 6 plus 2 aluminium. So if you rearrange that, you should get that aluminium is equal to +3. Okay, and then for iron, what should iron's oxidation state be in the products? So why, T-Boy, do you think the sulfur has an oxidation state of 2.5? So let's go through that one. Hang on. So iron is 0. Just a quick alteration to what we're about to do. So T-Boy says that S4O6 2- has an oxidation state of 2.5. So if we look at things with odd oxidation states, remember that especially when we're looking at oxygen in H2O2, oxidation state for oxygen changes to -1. So the rules aren't necessarily exactly the same every time, but in your exam, you're not going to be given something where you should have rules that you haven't learned. So if you're coming up with a half number for your oxidation states in your exam, you can pretty much assume that it's wrong. It's an average of different oxidation states in the compound. So if you're getting a mixture of things, of a solution with 2 different oxidation states, with 2 different compounds, then you're not looking at the oxidation state of the compound. You're looking at an average of oxidation states of 2 different compounds. If the oxidation state is different and you've had to average them, you have 2 different compounds. Okay, so at this point, we want to be thinking about what it means when an oxidation number goes up and what it means when an oxidation number goes down. So when the oxidation number goes up, has our element been oxidized or reduced? Yeah, oxidized. So when the oxidation number goes up, the element has been oxidized. And what does that mean for the electrons? What does that mean about our number of electrons? Yeah, it's lost electrons. So what in our reaction on the right-hand side, what has been oxidized? Yeah, aluminium. Thank you, Fassi. So if aluminium was oxidized, how many, looking at your oxidation numbers, how many electrons have been lost? Yeah. So aluminium has lost 3 electrons in the change of oxidation state. So that means that we probably think that the reverse is reasonably understandable. So when the oxidation number goes down, what does that mean? Yeah. So if the oxidation number goes down, the element has been reduced. Which means that we've, yeah, thanks, Aisha, which means that we have gained electrons. And in that case, what in our reaction has been reduced and by how many electrons? Yeah. How many electrons has, yeah, so iron has gained 3 electrons, or iron 2+ has gained, iron 3+ has gained. Okay, so T-Boy says, when something is oxidized, it acts as a reducing agent. Yes. So because oxidation means that you're losing electrons, it means that you're giving electrons to something else in a redox reaction. So if you're giving up electrons to something else, that means that other thing has been reduced. So when something is oxidized, it's a reducing agent. Yeah, it's really funny. I've never heard that that way of doing it, Pavathi. I've heard oil rig. Most of the time I've seen oil rig, oxidation is lost, reduction is gain. I've never seen Leoga or Leoga. But that's interesting. Okay, are we all happy? Anybody got any questions? Yes? Yep. Okay, good. All right. So at this point, we're going to be looking at how to construct full equations from half equations. So this is a bit of a rest of our oxidation numbers, and then we're going to come back to them when we go in the other direction from half equations to full equations. How would you do if nitrogen was in a compound? You would work it out the same way we worked out this one. You would use the rules you have already about oxygen and hydrogen and fluorine, and you would add up to either the charge if it's a charged compound, or you would add up to 0 if it's an uncharged compound. But it's no different. Nitrogen doesn't have any special rules. What if there's two unknowns? If there are two unknowns, it's very unlikely that you'll have two unknowns. If you've seen a question like that, it's likely that you have an ionic bond in there somewhere. So the assumption is that you know the charge of one side of the ionic bond and the charge of the other side, in which case you treat them separately. So I imagine if you've seen two unknowns, that's why there's been two unknowns. Let me know if that doesn't help, or if that does help. Okay, cool. So if we're looking at constructing full equations from half equations, there's sort of two things that we need to make sure of. Two things that we're going to do. Does anyone know sort of like what are the two things we do when we construct full equations from half equations? So what Happy Panda means by unknowns, as in like there are two compounds that aren't, two elements that aren't on the list of standard oxidation numbers. Those are your unknowns. Balance, yes. So you need to balance what? What are you making sure you're balancing? Yes, Jackie's got it. So balance the number of electrons transferred. Yeah, so Happy Panda, your NH4, you should be able to recognize is your ammonium ion. So you treat that as a different compound to your VH3, VO3 minus. So they're two different ones. So it's essentially asking you two questions rather than asking you to add them up overall. Yeah, so we want to make sure we balance the number of electrons transferred. What's the next thing that we do when we're going from half equations to full equations? Yeah, you're right, T-Boy. Ammonium has a charge of +1. Yeah, so you want to cancel the electrons. Thank you, Jackie. So we balance the number of electrons and then we remove the electrons from the equation. Okay, so let's have a go at the first one. So we're looking at and what kind of reactions. So what's happening to our iron 3+? Is it being oxidized or reduced? As in just the, yeah, it's being reduced. Okay, so we know that it's being reduced. And what about our tin? What's happening to our tin? Yeah. Okay, perfect. So do I need to do any balancing for these two equations? Are our electrons balanced? Yeah, all balanced. Okay, so I want you guys just to show me what is my full equation. I'm not going to write it, you guys are going to write it. So we know that the electrons are balanced, so the only thing to do at this point is to remove all of the electrons from the equation, because I've even kindly put them the right way round for you, so that's useful. Beautiful. So Aisha's got it. Anybody else? Can anybody improve upon that? What has Aisha not included and Happy Panda not included in their equations that should be in there? State symbols, yeah, we should also have our state symbols in there. But this one was a nice one because there was no balancing necessary, but otherwise we were totally correct. Okay, so the next one is slightly more tricky because we've not only got electrons in there, we've got some other things as well. We've got water, and we've got protons in our sort of manganese equation. Does anyone know, do we include the water and the protons, or do we get rid of them like we get rid of electrons? Anybody? Yeah, you keep them. So you have to keep, the only thing you're getting rid of is electrons, you're keeping your protons and your water. And T-Boy and Aisha were also correct. So they said that we need to times our iron equation by 5, right? Which is correct because we have the movement of 5 electrons in the manganate equation. So we need to times everything in the iron equation by 5 so that it can gain 5, lose 5 electrons. All right, at this point, you guys can go for it again. Go ahead and I think somebody asked what oxidation state nitrogen has in cyanide a little while ago. So nitrogen mostly has an oxidation state of -3. So if there's nothing else in there that can tell you what the oxidation state is, then you assume nitrogen has an oxidation state of -3. Cool, so Happy Panda sets 5, 2++, MnO4, yeah, with our beautiful state symbols. All but one state symbol. What happened to water, Happy Panda? What happened to my state symbol for water? But yes, you are lovely and correct, bar the state symbol for water, which if anybody wants to chuck in what that is. Yeah, it's liquid. Water is always liquid because of course if it was or solid, but it can't be aqueous because that would mean that it was dissolved into itself, which doesn't make sense. Okay, perfect. All right, so in that case, is everyone okay? Because we're going to go on to the sort of slightly more tricky, the slightly trickier version of things, which is going the other way around. So are we all feeling comfortable with full equations from half equations? Yes, no, maybe. Yeah, all looking lovely. Perfect. All right. So this is sort of the bit that people mostly find tricky. So we're going to have a go at these now. So the reason that we covered oxidation states at the beginning is because this bit relies on oxidation states. It relies on us being able to look at a full equation and figure out how many electrons has been gained or lost, which is fine if something has a really common charge. But if it's something that you haven't come across before in a compound or it has a charge that it doesn't usually have, then it's a little bit difficult. So we're going to look at how to do this. So the first thing we want to do is work out the oxidation states of all of our compounds. So for our manganese and manganate equation, we have oxygen, manganese, hydrogen, and chlorine. So in our in our first half of our equation, in our reactants, what is our oxidation state for oxygen? Anybody? Yeah, so Jackie, you're right. Let's go with oxygen first. Yeah, oxygen's -2. And if there are 2 oxygens and it's -2, that means overall it's -4. So add up to 0. Jackie is right, it is +4 for our manganese. That is, yep, cool. What about hydrogen in HCl? What should that be? So remember, just a note for the people that were sort of saying -4, when we're asking about the oxidation state of something, we're asking about the oxidation state of a single thing. So when we say oxygen and we ask for the oxidation state, we mean for 1 oxygen, not for 2 oxygens. So it's -2. But yes, so for hydrogen, it should be +1, and that's the standard. And for chlorine? Anybody for chlorine? Yeah, it must be -1 because hydrogen is +1. So to get back down to 0, we have to take away 1. Okay, so let's go again, but in the products. So we have oxygen, which is going to be the same. So I won't bother ask that. What about manganese? If manganese is with 2 chlorines, what must the oxidation state be for manganese? So remembering that chlorine has an oxidation state of -1. Yeah, so there's 2 chlorines, so that takes us down to -2. So to get back up to 0, we have to add 2. So we've got an oxidation state change for manganese of 2. And hydrogen, is hydrogen still +1? Is my hydrogen the same? Yeah, so +1, still hydrogen. What about my chlorine? Hello, Anaphyl. 0, yeah. So we want to talk about what's happened to the electrons in both manganese and in chlorine, because chlorine doesn't just have one state. So chlorine is both in its gaseous state, so just Cl2, which is an element, so it's 0, but it also is what? Where else is our chlorine in the products? Yeah, you're totally right, Jackie. Yeah, so chlorine's also in my, yeah, thanks, Rachel. Chlorine's also in my manganese chloride, which means that it still has an oxidation state of -1. So only some of the chlorine has had its oxidation state changed. Other bits of the chlorine haven't. So we'll think about manganese first, because that's slightly easier. So if manganese has gone from an oxidation state of +4 to +2, has it gained or lost electrons, and how many? Yeah, it's been reduced. So that means that what's happened with its electrons? Yeah, so manganese has gained 2 electrons. And what about chlorine? So chlorine hasn't lost 2 electrons because we're going from an oxidation state of -1 to 0. So that's only a change of 1, right? So that means that some of the chlorine has lost 1 electron, but only some of the chlorine. So at this point, we're completely ready to, so it's not both oxidized and reduced because it's oxidized because it loses an electron, but it also stays the same. So it's not necessarily reduced as well, it just stays the same. So some of it undergoes a redox, some of it just sort of stays. Okay, let's write out our half equation for manganese first. So manganese is gaining 2 electrons, right? So we just write MnO2 plus 2 electrons. And what do we form? Does anyone know? So remembering that we're not including, we don't want to include chlorine. So what charge is that manganese going to have? Yes, you're right. An element that is both oxidized and reduced is called disproportionation reaction. So we don't want to include chlorine, right? Because it's a half equation, which means the only compounds that should be involved. Yeah. And yeah, so Jackie's got it. So it's an Mn2 plus. And this is because our manganese is with 2 chlorines, right? And you should know from your studies of your halogens that they always have a 1 minus charge, right? So if we've got 2 of them, our manganese should have a 2 plus charge. And what else do I need to keep on in this half equation? There's something else I have to add. Yeah, the water needs to be in there as well. And if the water needs to be in there as well, what does that mean about the forward reaction? What else needs to be in that? What is now unbalanced? Yeah, H plus. How many? How many protons? Yeah, we need to balance the protons. So how many protons do I need in my reactants? 4, yeah. Thank you, Aisha. All right, perfect. So the only other half equation we need to write for this one has got to be our chlorine half equation, right? So in our chlorine half equation, we're going to be starting with what species of chlorine? Yeah, but do we include the hydrogen? Yeah, thanks, Jackie. So it's just going to be a Cl minus. We're going to have a Cl minus. And do we need to include electrons in the reactants, or are they in the products? Yeah, no, they're in the products. Thank you. So we're going to have, what is our product going to be? So T-Boy says our product's going to be Cl2, which is totally correct. And if we have Cl2 in the products, how many chlorines do we need? How many electrons do we need? Yeah, we need two chlorines, and it must be 2 electrons, right? Because if we've got 2 moles of chlorine, we also have 2 moles of electrons. So Aisha says, why is oxygen included in the manganate? Because manganate is not an ion. So there's no, it's not the oxygen is like a spectator ion, or it's not the oxygen isn't part of that half equation. So this is the main case that you'll see where other stuff is in the half equation when you have oxygen bonded to something and it makes water. Okay, is everybody feeling comfortable with that? Because if so, what I think we're going to do is go ahead and do the exam question, because I don't think we're going to have time to do the other half of this. So I suppose at this point is, how are you feeling in general about the whole thing? So why is H not included? In which one, Aisha? Because H's protons are included in, so if we include oxygen in the manganate, that means for the equation to be balanced, we also have to include what happens to the oxygen. So it creates water. So we have to include water. Water is not an ionic compound, it's a covalent compound. So we have to include the hydrogen in that. And then if we've included the hydrogen on that side, that means we also have to include the compounds on the left-hand side. So it's about the difference between something ionic, where it's an ionic bonding system, so we don't need to write both because it's a half equation, versus something when it's a covalent bond, and you do need to keep the covalent bonds or something with a covalent like quality in the reactants. So why is the oxygen included in the, because the hydrogen chloride bond is, the hydrogen is not involved in the oxidation at all. Does that make sense? Like the hydrogen has no role to play with the actual oxidation or reduction reaction that's happening in that case. Whereas with the manganate, the proton is involved in the oxidation and reduction. And it's pretty easy for A level because basically the only situation that you'll see, or mostly the only situation you'll see the inclusion of oxygen and protons and water is with the manganate example. So as long as you remember that one, you'll be all right. Does that make sense at all? So I'm gonna move on unless there's no, no, it doesn't make sense at all. I think what's the best way of putting this? Because we're talking about the oxidation, I think the best way for you to think about it is probably that if you're talking about an oxidation reaction and something is bonded to oxygen itself, the oxygen takes part in the oxidizing step or the reduction step in a way that other things don't. So if something is involved in the actual oxidation, then you have to, or the reduction, you have to include it in the half equation. If it's not involved in that specific half equation's reduction or oxidation, you don't need to include it. Does that make sense? Still no? I could say that, but it doesn't explain, that wouldn't explain why the oxygen is there in the first place. So how do you know if it's important? If it's involved in the oxidation. So if it's oxygen, it's likely that you're going to keep it in there. That's basically all I can say in terms of A-level science. If it's oxygen, it's likely that it's involved, so leave it in. And again, the one you're most likely to get is manganese and manganate. You may get vanadium as well, so like V2O3. So if it's oxygen, essentially oxygen is the one that you're going to be keeping in there. There's going to be nothing else that you keep in your half equations apart from when oxygen is bonded to something else. Does that help? If it doesn't help, if you're still feeling confused, I think what I shall do is I won't be able to address it here and now, but I will have to think about a better way to explain that in terms of A-level. And then the next time you're in a YouTube class, I'll have a quick go at explaining it again, because I can see that it's still confusing you. So that's what I'm going to do actually. Next YouTube class, I'm going to like think about a better way of explaining this, and then you can help me workshop my explanations, but we should probably get on with the exam question. Because remember that for teachers, every teaching people things is trial and error. So sometimes you have to think more about how other people think of things to be able to explain it. So I will do that. All right, so we're going to do the exam question, or we're going to run out of time. So chlorine is formed when potassium manganate reacts with hydrochloric acid. The ionic equation for the redox reaction is the following. So we've got 16H+, and we've got 2 moles of manganate and 10 chlorine ions, and then we end up with Mn2+, and 8 water molecules and 5 Cl2. So the first thing is to deduce the half equation for the oxidation of chloride to chloride ions. Yeah, and Jackie's got it right off the bat. Chlorine is reasonably easy because we all know the charge of chlorine. So we could think of it in terms of oxidation states. We could think of it in terms of, we know that Cl- must have an oxidation state of -1 because it's minus, and we know that Cl2 must have an oxidation state of 0. So we know that it's going to have lost electrons. And because it's Cl2, you need 2 chlorines and 2 electrons. So the next part says, give the oxidation state of manganese in the MnO4 minus. So does anyone want to sort of take a stab at that? Yeah, it's going to be +7, right? Because we've got 4 oxygens, so it's -2 times 4, which is 8, and we need to add up to the charge of -1. So to get from -8 to -1, we must add 7. Okay, so at this point, we know that manganese has lost or gained 7 electrons. Yeah, so Fassy's got it. So it's gained 7 electrons, because if you think about it, remember that a decrease in oxidation state means that okay. So if we decrease the oxidation state, what does that mean? Has it been oxidized or reduced? Yeah, it's been reduced. So the oxidation state of manganate here is +7, and the oxidation state over here must be +2, right? Because it's a 2+ charge. So if it's been reduced, that means that it's lost or gained electrons. Yeah, it's gained electrons, right? So we have gained how many electrons for manganese? Perfect. Yeah, we've gained 5 electrons because we've gone from a +7 state to a +2 state, which means that we've gained 5 electrons. So I'm going to put in my manganate with my oxygen, because that's the rule, keep it with its oxygen, and I'm going to have 5 electrons. And you guys are going to tell me, you're going to write the rest of it. What's the rest of my equation? Yeah, so I'm getting like bits and bobs, but I would like it on the right side. Yeah, so I've got lots of people saying +H+. So yes, we do need +8H+. And as the equation, the full equation above says that we have Mn2+, and we also have some water. So if we've got 4 oxygens on the left-hand side, it means that we must have 4 water molecules, which means that we'll end up with a total of 8 protons. Okay, so that's going to have to bring us to the end today, because I've kind of run over. Do we have any questions? No questions? Okay. In that case, I really hope that was useful. Is this class every Thursday? Yeah, from now on. When will the poll be open? I'm not sure. But if you're sort of like subscribed to the notifications, it will pop up. You're welcome, Jackie. What about 2 Mn2+? You don't need 2 of them, because in the reactants we only had 1 manganese. Can one substance be both oxidized and reduced? Yes, it can. It's called a disproportionation reaction. You're welcome. I will see you guys next Thursday. I will think about how to better explain the inclusion of oxygen, and I'll get back to you on that. What's the hardest thing they can ask? Rachel, that is such a wide question. It really depends on what you find. In the reaction, there is 2. Yes, that is true. There are 2, but you're writing a half equation, which means that it doesn't have to be balanced with the chlorines. It only has to be balanced with itself. So you don't need two moles. How do you know if the metal's charge matches to the oxygen's charge, or if the oxygen's charge will match to the metals? I don't know what you mean by that question. Jack, that's a bit of a confusing question. Can I give an example of a disproportionation reaction? Yes, I can. So usually it's chlorine, but let me try and remember what it actually is, because it's been a while since I had to like do it on the fly. So really quickly. Yeah. All right. So chlorine has a disproportionation reaction. That is when it's reacting with sodium hydroxide, and it creates NaCl, but it also creates NaClO and water, which means that the chlorine goes from an oxidation state of 0 in its element. When it's with sodium, it goes to -1, but when it's with the oxygen and the sodium, it goes to +1. So it's both oxidized and reduced. Jack says, so to calculate oxidation state of manganese, we look at the charge on the oxygen, right? So we're not looking at the charge, we're looking at the oxidation state and adding up to the charge. So it's not, so we add up to the charge in total, but we don't add up. So the charge of that whole thing is -1, right? I said, so if, hang on, I'll get back to you, Aisha. So if the charge is -1 on the manganate, we're looking at the oxidation state of oxygen. The oxidation state of oxygen is almost always -2, right? So we have to we use oxygen and we times oxygen's -2 by the number of oxygens, which is -8. And we have to add up to -1 because there's a -1 charge. So if manganese plus -8 has to equal to -1. So if I do manganese -8 equals -1, and then I take over the -8, we get that manganese is equal to +7. So it's not to do with the charge of manganese and oxidation states. So Aisha says, so if it asks for a half equation for chlorine, which one to use, chlorine plus or chlorine minus, you would write 2 different half equations, Aisha, because you have one oxidation reaction, one reduction reaction. So you want to write 2. Disproportionation means something is both oxidized and reduced, but I have to leave it there, guys, because I have another class, so I have to go. But it was a pleasure having you, and we will do this again next week. Have a lovely evening. Pavathi, put that down as a topic, a tricky topic for request that on Insta, and maybe we can do that in another class. Bye.